Okay, so welcome once again. Now, the aspect of physics that I'm going to treat today is from the mechanics part. Now, realize that all of physics that you are going to learn begins with mechanics. So there's no way you are going to understand heat and properties of matter deeply if you do not understand some of the contents of mechanics. In the last class, you remember that when you tried to define temperature, some of you said, okay, temperature is a measure of the degree of hotness or coldness of a body. And then I did query, how do you quantify that? How do you measure it? How do you express it in terms of numbers? Then we ended up realizing that when a body becomes hot, or as a body becomes hot and hot, or hotter and hotter, the constituent particles move faster and faster. So therefore, we defined temperature as a measure of the average kinetic energy of the constituent particles. Now, the matter around you, which is either in solid state, liquid, or gaseous state, comprised of atoms and molecules. Now, these molecules are the constituent particles of these your objects that you talk about. And then when you hit these objects, these molecules increase the average speed. All right? Now, the motion of these particles, or all these constituent particles, can collectively be referred to as thermal motion. So in other words, at the heart of everything we are going to discuss is motion. So you have to understand what motion is about. So, but you know that for you to be able to discuss motion, you first of all have to be able to know how to locate an object. So how do you locate an object? So imagine that you wake up in a room that is very dark, right? From your bed, and then you know in your mind where the table, your reading table is in the room relative to the bed. So if you want to pick your cell phone that you left there, the very first thing that you think about will be how to locate the table. So to locate the table, you have the bed as the reference point. So if you have known ab initio that your bed is located to the right-hand side of your bed, then you know how to start out, okay? So in other words, to be able to specify the position of an object in space at all, you have to have a reference object or a reference point. Now, such an arrangement in which we have a system of coordinates that allows us, that's attached to an object, which we call the reference object, that allows you to locate the position or define the motion of another object relative to it, is called the frame of reference. Now, you know that the universe in which we live comprises of a very vast expanse of space and contains matter in various states. All right? The space in which we live, that is the universe in which we live, is made of a vast expanse of space and contains matter in various states and forms, if you like. Now, you also know that the bulk properties of matter are the result of motion, interaction, and arrangement of atoms, or molecules, or electrons, or if you like, the constituent particles that make up the object. Okay, you know that. So now, mechanics is a branch of physics which studies the motion and interaction of matter. I have used two terms there, motion and then interaction. Now, it provides the basic foundation needed to understand the properties of matter. Now, before I go on, I use the term bulk matter. When I say bulk matter, we are talking about matter in a form that is, okay, if you like, visible or realizable by touch. You can touch it, okay, or you can feel it, okay. So, for instance, if we talk about the heat, that's which is a measure of the energy, okay, content of a system, or the energy that flows from place to place as a consequence of the difference in temperature as we defined last time. Now, this is what you can measure, meaning that you can see it or you can measure it. It becomes bulk property. It becomes the bulk property, or even the temperature that you talked about. All right? So temperature is a bulk property, but it is a consequence of the motion of particles that you cannot actually see directly. Okay? So, but you know this, you can infer some of the results that you obtain from the observation of bulk property. So when I use the term bulk property, I'm referring to such quantities as the temperature, pressure, density, and all that. These are bulk properties of any substance or matter. Okay? So that's what you have to be, keep at the back of your mind. All right. Now, I'm saying that temperature is a measure, heat is a form of energy which flows from place to place as a result of the temperature gradient between those 2 points. From place to place, from place to place means from one point to another as a result of temperature difference. So if I use the term gradient, I'm talking about the slope. One is at a higher level, the other is at a lower level. So if I put a ball at the high level, the tendency is for it to run down slope, isn't it? So therefore, I'm saying heat is a form of energy which flows from place to place as a result of the temperature gradient between them. So if I'm using the term gradient there, I imply that heat will flow from the region of high temperature to the region of low temperature. So the gradient is from high to low in this case, as if you are going down the slope of a hill. All right. Now, temperature is also a measure of the average kinetic energy. Temperature is a measure of the average kinetic energy. We've talked about that, of atoms, molecules, of an object, and all that. Now, heat and properties of matter is therefore the study of the bulk or macroscopic properties of objects arising from the motion, as from mechanics, if you like, at the microscopic level, that's at the atomic, molecular, or even subatomic level. All right, so take note of that. Now then, now motion itself, what is it? It is a change in motion, a change in position of an object in space with change in time. Therefore, the fundamental or basic concepts involved in the description of motion of an object is space first and then time. So in other words, space and time form the basic, backbone, if you like, the backbone of every discussion that touches on motion. Because if you cannot locate an object in space, then you cannot talk about the change of its position with time, and therefore you cannot describe motion. So in this class, we will learn how to locate an object in space and how its motion may be specified. Okay, so in other words, the topic that we have to discuss here is simply space and time, or if it's in your course material level that way, it should be space and time. That's the course material that you have online there. That is the mechanics part, the elementary mechanics part. Okay, now so we will begin with mechanics and then go on to look at the concepts. We apply the concepts we learned to properties of matter. Of course, I've already started doing that. So I'm taking the two side by side in order to free myself from blame, in order to vindicate myself. Because tomorrow, if anybody is setting questions, you will say, okay, this part was not taught. That part was taught. So I'm going to endeavor to touch the two parts. But like I said, you will have to read a large part of the second part, that's the B part, which is the one that you have in your hands. That's heat and properties of matter. I expect you to be in unit 4 by now. Because if I look at it, the very first part is descriptive. You were talking about temperature, and then the second unit was thermometry, types of thermometer. So therefore, I'm not going to come and teach that in this class. That is something that belongs in a secondary school class. So I expect you to read that by yourself. I will never discuss with you, or I will never teach that, but I can discuss with you anyway of thermometry. That's types of thermometer. So you better read that on your own. Then the next part, the third part is the third unit, if you like, talks about measurement of heat. I will touch on that. Now, measurement of heat, of course, we are talking about things that you already know. We'll be defining such quantities as specific heat capacity, specific heat of latent fusion, latent heat of fusion, of latent heat of vaporization and all that. You've heard all of that. That's when there is change of state. So we are going to look at that. I will do that briefly. Then the next part has to do with thermal expansion. Now, the equations are exactly the ones that you've studied in secondary school. So I will not bother to teach them. I will simply write down the equations and apply them to the kind of questions that we expect you to be able to answer in your TMA, or for that matter, at the end of the course material, the exercises. All right. Now, so I'm saying that we'll begin with mechanics and then go on to apply the concepts you are going to learn to properties of matter, that's heat and properties of matter. Now, you may ask, why do we even start with mechanics? Well, one answer is that every other aspect of the study of physics will always be resolved to things that make sense to us on a day-to-day experience. So in other words, what I'm saying is, if you know what happens to you when you are in a moving car, or when you are walking, or when the wind is blowing on your face, then you'll be able to describe a similar experience if you were to be reduced or to reduce your concept to the atomic and subatomic levels. So if you do not understand the description of motion to the common experience that we have, you cannot describe it at the level that you have to imagine. So therefore, we always start with mechanics whenever we are teaching physics, because mechanics is very closely related with our common experience on a day-to-day basis. That's why we start with it. Now, let us go on to the concept of space and time that we are introducing. So we expect that the learning outcome should be that at the end of this, you should be able to list the properties of space and time, explain the concept of frame of reference, explain what is meant by inertial frame of reference. That's from the term inertia. And then explain what is meant by perform simple Galilean coordinate transformations. I'm going to teach how that works. Distinguish between non-inertial and inertial frames and demonstrate the relationship between the Cartesian and the polar coordinate system. All of that are found in your course material. And then you discuss the concept of space-time coordinates. I have added this for the sake of those that may most likely come to study physics. You see, when we are talking about space and time, all right, an event in any point in our physical universe occurs at a position, a certain position in space, and that occurs at a given time. So in other words, you cannot separate between space and the time of occurrence of an event. All right, so that's why I decided to bind two of them, as is commonly done in physics, especially in the aspect of physics called relativity. We call it space-time. And so the coordinates now become space-time coordinates. I will solve simple examples to illustrate that. All right. So now, space is one of the fundamental concepts in physics. Take note of that. Now, you already know when we say fundamental or basic, we mean that such concepts cannot be broken down to much simpler concepts. A basic concept means other concepts can depend on it. So such a concept exists itself independently. Of course, in mathematics, you know, the ones that we call when you talk about functions, of course, a dependent variable and an independent variable. So that's not what I'm talking about. I'm saying that a fundamental concept is a concept that does not depend on another concept in a way. So in other words, its measurement is determined, right, independently, and then all the other measurements that have to make use of it will depend on it, what we have found for it. So we'll come to that. Now, the other basic units are time and mass. Now, these are the fundamental quantities in the sense that they cannot be broken down to simpler concepts. Now, in your senior secondary school, you studied what you call the fundamental quantities. The fundamental quantities. Perhaps I should I'll unmute you at this point and find out what you know about that fundamental quantities. Let me unmute you. How many fundamental quantities do we have? How many? How many of them?
7.
We have 7 fundamental quantities.
Very good. 7 of them.
We have 7 fundamental quantities.
We have mass.
7, yes, let me hear them.
Fundamental quantities.
We have time.
We have time. Mass.
Temperature. Luminous intensity.
Amount of substance.
Amount of substance, yes. I've not heard 2 of them.
Electric current. Electric current.
Electric current.
Electric current, yes.
Luminous intensity.
Length.
He has mentioned that earlier. We have another one of them is left. You have mentioned 6 so far. I didn't hear temperature. Temperature.
Times speed.
So you have length, mass, time, and then electric current, temperature. That's 5. Luminous intensity, and then substance. All right.
Electric current.
Yes. Okay. So that's very good. You know all of this.
Temperature.
All right. Now let us go back to the script. All right. So, all right. So now the concept of space is associated with position. That's location of a position of an object in space. So once you are talking about space, you are talking about location or position. That's what it means. I hope that is clear to you. Now, once we talk about space, we are talking about how you can locate the position in any portion of the universe. So in other words, space, in a sense, is any part of the physical universe in which we live. Any part of the universe. It could be far away from us. It could be very close to us. All right? But now, even the earth on which we are walking around is located in space. And it is even part of space. Because to another planet, somebody in another planet there, even in our solar system, it will be talking about outer space. All right? And then the earth where we live is part of its outer space. So in other words, any portion of the physical universe in which we live, all right, can be referred to as space. Hello, sir, I will call you back. I'm in a class. All right, so you know that now. Any portion of the physical universe constitutes what you call space. And the most important thing about space here is how do we locate the position of an object anywhere in space, okay? All right, so now, so therefore space refers to, or is about, the study of space here is about how can we locate an object or an event in any part of our physical universe where we have natural phenomena occurring. Now, in classical mechanics, space is considered to be real and has the following properties. It is infinitely large, one, and that is, it is endless. So what you refer to as the universe today is the universe to the extent that we can see. To the extent that we can see aided or unaided. So now when we can see stars at night, but then some of them are too far that we cannot see them without the help of telescope, right? But now the limit of the universe that we can see, all right, is limited by the resolution, if you like, of the telescopes that we can use or that we have, the technology that of the telescopes that we are using presently. Now, 3-dimensional. Now, we are saying that space also is 3-dimensional. Now, a point in space is suitably given by 3 numbers representing its coordinates. Any position in space can be given by 3 numbers, whatever the coordinate system you have taken. Well, mathematically, you will realize that we may locate, we may have more than just 3 3 points like this that I have talked about, but I will just give us what is common to our physical experiences, and that is that space is 3-dimensional, meaning that any position in space can suitably be given by 3 points or 3 numbers, beg pardon, 3 numbers representing what we call the coordinates of such a point. Now, space is also continuous. That is, there are no breaks between its parts. Okay, there's no space. Of course, when you are in flight, you notice that there's nothing that obstructs your motion there. Why we have obstruction on Earth is that, of course, the buildings, the trees, and all that seem to make space not to be continuous. But in reality, space is continuous because all the matter that constitute part of our universe is also part of space anyway. Now, space is also homogeneous in the sense that all its parts are identical or uniform. So take note of that. When we say something is homogeneous, it means all its parts are uniform. That's they look alike in every respect. Now, space is also isotropic. The word isotropic here means that its properties are the same in all directions. So if we were to remove all the houses, all the trees, all the objects, then everywhere will look alike, okay, to us. I don't know if you have seen this before. During a Harmattan period, and you find yourself in an open space, and you are surrounded by thick haze, and you cannot see maybe more than 1 meter or 2, or maybe a little more than that. You notice that everywhere look alike to you. Okay, so that's what we mean. All the properties of space will look the same in all directions. So once that happens, we say that such properties are isotropic. Now, let me stop at this point and draw your attention to the fact that in physics, as in any discipline, we always also have to develop what we call the register. That's the language, the terminologies, which constitute the register. You have it in law, in journalism, in medicine. So physics cannot be exempted from it. So take note of the terms that we have used. Take note of the terms. Because if you are using any other terms, they may not be quite suitable in describing the concept that you intend to discuss. All right. So we said space is isotropic, meaning that the properties of space are alike or look the same in all directions. Now, apart from this, we also can take a look at time. I just want us to hurry up. Now, time is associated with duration or succession, okay, of an observation or event. Time, as a fundamental concept, is associated with duration and succession. And it also possesses the following properties. One, it is infinitely large, that is, it is endless. Of course, if you turn on the watch, turn on time, even if the watch stops, the time continues, all right? It is one-dimensional. That is to say, it flows from the present to future. So it's one-dimensional. It goes in one direction, all right? Now, continuous, it flows continuously. It does not stop, and it is also homogeneous, all right? So, and it is irreversible. So when you've lost the time that you should have done something now, you cannot regain it. Now, the time between two events is called the interval of time. And the limit of time interval tending to 0 is called the instant of time. So if we are looking at an event, okay, that's making an observation in a time interval that is very, very small, then we are saying that that event occurs at an instant of time. The word there is instant, all right? Now, the concept of mass is associated with quantity of matter in and a measure of the inertia of a body. So there are 2 terms there. The first thing is that it is a quantity of matter. So if I'm given a cube, a 1 cm cube of lead and 1 cm cube of wood, you notice that 1 cm cube of lead will be heavier than 1 cm cube of wood. Reason, because the lead, 1 cm cube of lead contains much more matter in it than 1 cm cube of, okay? So we'll talk about that when we are discussing the concept of density. Now, so That's what we mean when we talk about mass. So now mass is constant in time. As far as we are not talking about motion of an object at speed close to the speed of light. Okay? Those of you that will be studying the physics of relativity will come to realize that when we are observing the mass of an object at speed close to the speed of light, such speeds are called relativistic speeds, then mass will increase with speed. As our speed increases, mass will also increase. Now, we are not going to deal with that here. So that's why I'm saying that mass is constant in time. That's as time goes on, it does not really change. Now, I've also pointed out about the relativistic speed here. So, and in our study here, we will treat an object as a particle. A particle is simply a point mass. So it has mass, but its extent, its physical extent is negligible. I hope that is that like a pencil point, if you like. All right. So the mass, it has mass, we'll consider its mass, but its size is negligible. Now, apart from these three basic notions, which are relevant in mechanics, now there are four other fundamental notions which you all have already named. So now let us go on to location of an object. I did say at the beginning that for us to be able to locate an object, I will give you time, those of you that are making marks on the script here, when I'm going to draw, I'm going to put it directly on that thing that you are drawing there, since you have access to the script. Okay, so you can make the marks, but I'm also going to draw and superpose on it so that you can see it clearly. Okay, I'm not going to remove it since you don't take instructions. Don't remove it, put it there. I'm going to draw directly on those diagrams, those things that you are drawing, so that you learn discipline. All right. Now, how can we specify the position of an object in space? That's the most important thing here. Now, to specify the position of an object in space, we require a frame of reference, or what we call the reference frame, or the reference object. I've already mentioned that. And I gave an example of how you can locate the position of a table in your room if you wake up in a room that is completely dark, and the only reference object is your bed. So you can know from your bed whether the table is located in front of you or to the right or left, and then you know how to make your way there. Now, a frame of reference is a coordinate system attached to an object relative to which measurements are made. A coordinate system consists of a reference point or origin and a set of mutually perpendicular axes, that is, straight lines in mutually perpendicular directions. Now, in the Euclidean geometry, the position of a point in space consists of a three-dimensional Cartesian coordinates, that's x, y, and z, as shown in this figure. So look at my figure 1 there. Now look at it. So now to locate position of a point P here, now you notice that I will have to move along the x-axis, parallel to the y-axis, and then parallel to the z-axis this way, isn't it? So therefore, the position, the coordinates of the point P has to be an ordered triplet, an ordered tuple. Now, an ordered set like this is called a tuple in mathematical language. Now, if it's just you can say, okay, an ordered, what do you call them? Two triplets is 3. The other one is a twin. All right. Yes. Duplet, Abi. Yes. An ordered duplet if it's 2. Ordered triplet. The general word here is called tuple. Let me write it down here so that if you are reading any standard text, you will see the term and it will not be new to you, tuple. All right. All right. So that's how it is spelled. Okay. So, and it is another tuple. What I mean here is that in order to get to point P, you move first along X, then parallel to Y. You see, along X like this from the origin this way, then parallel to Y like this, along this direction, and then parallel to Z direction. Always in that order. So that means these. Now it's a set in the sense that I enclose it, all right, by this bracket, and then I separate all the elements with these commas. Take note of that. This is how it is represented. All right. So realize that the coordinates of point P, X, Y, Z in space is an ordered set representing the sequence of steps taken to go from the origin O to point P as shown in the figure. All right. I hope you understand what I've done there. All right. So now I'll go on to something else. Give me a minute. Let me wipe this and make space. So now, oftentimes you notice that in your TMA questions and in your opening part of the course material, you notice that there's this diagram. This diagram is drawn here to allow us to have an idea of how we can relate the position of a point in space to two observers, one that is stationary in space, if it is possible, and the other one is moving at constant velocity relative to him, okay? So now in this figure, you can see that we have two reference frames. One is S, the other one is S prime. And then we have observers at the origin. So the observer is here, O, and in this other frame is O prime. Now each of these frames of reference has three axes, X, Y, and then the Z axis as I've arranged. Would have been arranged any other way around, okay? So things like this are called frames of reference. Now frame of reference which are in translational motion at constant velocity relative to each other, all right? So such frames are called inertial frames of reference. Inertial frames of reference. So you will see this in the opening part of that your course material. But the most important thing that I want to draw your attention to is how the observation of an event at point P here is related, okay? To this one and this other one, that's to this observer and this, all right? So to the observer in the S frame, that's to O, he is going to measure the position of P as X, Y, Z. To the observer in the moving frame of reference O prime, S prime, I beg pardon, that's the observer O prime. The coordinates of P are X prime, Y prime, Z prime. So now the observer at O and O prime are equipped with measuring instruments to determine the coordinates of an event at point P. Now, measurement of the coordinates of the event at point P made by the observer in the S frame, that's X, Y, Z, and T, that's T being the time during which he makes the observation or measurement, and the ones made by the observer in the moving frame are related by these transformation equations. Okay, so it's going to be X prime is equal to X minus BT, Y prime is equal to Y, Z prime is equal to Z, and T prime is equal to T. Now, let me show us why it should be like that. The reason is that the motion that we are observing here is along the x-axis, the common x-axis, the common x-axis here. So you have this one is translating to the right, okay? So now by the time it has moved a distance given as VT here, all right? And then the observation is made by this one and by this one. The relationship between this set and this set is given by this transformation equation. So this is a transformation equation here. All right, the coordinates of point P measured are related by that. So I'm going to take us to just one problem of that kind, and then we'll round up this discussion on this one. Let me see if we have a problem there that I've included. I want to give us a simple one that we can all answer. A passenger in a moving train. A passenger in a train moving at 20 meters per second observes a man standing on top of a flat roof of a house at an initial time T prime equal to T equal to 0 Now, 10 seconds after the train passes, the man on the roof observes that a bird flying along the track, that's along the track of that train, in the same direction as the train, is 300 meters away. 300 meters away. What are the space-time coordinates of the bird as determined by the passenger? The passenger is the person inside the train. Right? I want us to choose an answer. Or do I allow you to solve that? It's an assessment question. Let me unmute you and have your answers. Can I hear your suggestions on that?
So how can we solve this problem?
How you can solve it? Yes. Now the motion, look at it. We have already written the equation. Look at the equation here.
Do you have a
I've written the
formula?
equation that helps you. Look at it here. So this is what I'm asking you to apply. Can you see this?
Yes, sir.
So now let us look at, let me draw that for you. Let me just sketch something that will help you to answer it. I have very little time to spend on this in this class. So that's why I have to be very fast. So this is the train. The train is going this way. That's the bird. The bird is also flying this way. All right. So this is, so for somebody inside the train, there's somebody inside the train. So that's the passenger inside the train there. All right. Then somebody else.
Yes, sir.
Okay.
It's on the roof.
Yeah. Now you can be here. All right. So relative to you, you see this bird as flying. All right, in this direction. And relative to you, if you are stationary, you also see this train, or if you like, this passenger as moving in this direction. Does it make sense to you now? Okay. So,
yes, sir.
But relative to the passenger here, he sees this bird as moving this way. That is, if this train is moving at a speed of 80 kilometers per hour, for instance, 80 kilometers per hour, 80 kilometers per hour. While the bird is flying at what? About, let me say, 20, like 30 kilometers per hour. So, relative to the passenger inside, we are not paying attention. I will finish this at 2 of an eye now. So, relative to the passenger, this bird,
Sir, please mute everybody. Mute everybody, please.
Sir, mute everybody, sir. Mute everybody.
No,
I am asking questions at the same time. That's why I am muted all of you. I'm asking questions and I need answers.
Who is having that background noise now?
Don't worry. All right. So, all right. So relative to this passenger, this bird is flying in the opposite direction with a speed equal to 80 kilometers per hour minus 30 kilometers per hour, which is 50 kilometers per hour. That's how we will see it. But relative to a stationary observer, this man here, this one is flying to the right with a speed of 30 kilometers per hour, while this one is flying with the speed of, it's moving with the speed of 80 kilometers per hour. So if I were to ask a question now, relative to the bird, what do you, I would, if this is an individual now, relative to him, this one is moving to the right. Can see now? That is relative to the bird, okay? The train or the passenger in the train is moving to the right. Relative to the passenger in the plane, the bird is moving to the left. Relative to a stationary observer, both the bird and the train are moving to the right. So if you have that at the back of your mind and these transformation equations, so you assume that the train is moving in the positive x direction, okay? You should be able to write down the coordinates here, given this. Now, we are talking about the moving, we are talking about the person in the moving frame, meaning that we are talking about the position of the bed, all right? X prime, not X. When we are talking about the person moving now, in the moving frame, the coordinates will be X prime, Y prime, Z prime, and T prime. So the time will be the same for both of them. So therefore, it is this that you are going to transform. So transform these, transform the X coordinates, and let us have the answer. What do you have? Do I leave that as an exercise for you to take home? If you see it in your TMA questions, you should be able to answer that without any waste of time. All right. So I will leave it. Since it is a TMA question as an assessment question as I get. But I've given you a hint on how it could be done. All right. So any more? All right. So now let us add one more thing before we close. Let me introduce one other thing here, because I have to go very fast. Give me a minute. Let me share what I want you to see. The correct file. I think I can remove this. All right. Now, I want to share with us one more content of that your material, which I want you to see. Whatever you are reading there should be part of what I'm going to show us now. All right. So at the end of this part, you should be able to understand or explain and explain what is meant by physical quantity. And you should also be able to explain what is meant by measurement and units of measurement. And you should be able to use metric prefixes for multiples and submultiples of standard fundamental units. I will tell us what that means. And you should also be able to estimate what we call orders of magnitude of quantities if we have time, and distinguish between fundamental and derived quantities. You already know this part. If there is time, perform simple dimensional analysis of physical quantities and carry out checks on dimensional consistency of physical equations. So that's quite ambitious. Let me quickly share that with you. Just for okay, can you see that? Can you all see this? So now I want us to, can you see the board? Let me be sure you've seen the board or the screen. Can you see the screen?
Yes, sir.
Yes, sir, we can.
Yes, sir.
Yes, sir, we can see.
All right.
Sir, we can
Can you please see the assignment again, sir?
Yes, sir. Yes,
Yes,
sir.
sir. Yes, sir. It's in the screen,
I
sir.
think by the time you have started, you are telling me.
Yes, sir, we have seen the screen. We have seen the screen,
Please
sir.
listen. Please
It's
listen.
okay.
By the time you have started,
Yes, sir, we
you are
can see the
telling me.
screen.
It's easy for me to also direct whatever I'm doing to
Yes, sir, we can see the screen.
content of your email, so that please pay attention. Pay attention.
Yes, sir, we can see.
Sir, please mute everybody, please, sir, please.
Who said his time is off?
Well, I will stop you at the appropriate time anyway. There are 212 of you now, about 212 or thereabout. All right. So, you see, all the laws of physics that we are going to study are made of simple statements. All right? Simple statements like the relations, a statement relating force to acceleration. Okay, for instance, isn't it? So the laws of nature are simply concise statements of how nature behaves in any given circumstance. So now these laws consist of mathematical relationship amongst the physical quantities. So that means we have to understand what we mean by physical quantities. An example of a a law of nature is F equal to ma, which is Newton's second law in this form, as you will later understand. What this means is that there is a rule by which the size of one quantity is related to the size of another quantity, or a combination of other quantities, okay? And it is through experimentation that we can find out how they are related, okay? So experiments can help us to determine how quantities or set of quantities are related with another. Now, in this class, you should be able to, we are going to learn about physical quantities, measurements, and units and dimensions. So you should be able to explain what is meant by physical quantity, measurement. I've already stated that, fundamental and derived quantities, and so on and so forth. All right. Now, a physical quantity is the expression of an observation. The expression of an observation in terms of numbers. That's what we mean by a physical quantity. Now, that's a very simple definition that I've given. In everyday discussion, all right? Now, let me bring this down so you can see it clearly. I hope you can see what I'm saying. A physical quantity is the expression of an observation of a natural phenomenon in terms of numbers. All right. In other words, a physical quantity is a numerical description of a physical concept or phenomenon. In everyday discussion, we often hear such descriptions as very tall man. You see, if you have somebody that's tall and I ask you to describe him, you will say it's very tall. Or you can say the distance you have walked is very long distance. Or you can say a piece of object is very heavy piece of stone, etc. Such descriptions are not concise. They are subjective because what is heavy to one person may be light to another person when he's carrying it, isn't it? So such descriptions are subjective. They are not concise. A precise description of an observation is one that has been expressed in terms of numbers. Let me give you an example. If you say a 2 meter tall basketball player, 2 meter tall basketball, that means we can put the person, all right, against the wall and put a meter rule over his head there, and then we can see that he is 2 meters tall, okay? Or you can say a 100-meter dash, that somebody runs from here to there, and then we can measure the distance is a 100-meter dash. So you cannot say it's very long distance or very short distance. We give it in terms of numbers now, 100 meters. Or we can say a 50-liter fuel tank. You see, there's a number, and then there's a description attached to it. The description here is the unit, okay, of measurement. And I'm coming to that, okay? Now, the basic or fundamental physical quantities are those that are defined only in terms of the measurement directly. Examples of such quantities are length, mass, time. Other quantities may then be obtained by suitable combination of these fundamental quantities. You know that. Now, we said earlier on that laws of nature, a law of nature is a statement of the rule of combination of physical quantities to explain observed natural concepts of phenomena, and that these laws are mostly obtained through experimentation. That's what we said, all right? Now, an experiment consists of a set of measurements. But what do we mean by measurement? What is measurement? Now, measurement, if I should try to define it, is an act of comparing a physical quantity with a fixed quantity of the same kind to determine its size. I will repeat that. Is comparing a physical quantity with a fixed quantity of the same kind. That's the most important thing there. All right. Now, a fixed quantity with respect to which other quantities of the same kind are measured is called the unit of measurement. All right. Now, examples of different units of measurement of length could be found in different communities. It may differ from community to community. How would you, if you don't have a meter rule, okay, measure the length of yam tuber? All right, how will you measure it? All right, how will you measure that? How would you measure, how do the corridor football players measure the size of the goalposts? You know what we call corridor football in Nigeria here. You know, boys just coming to the corridor or coming to the open space, and then they want to put tire here or their slippers or whatever to mark the goalpost. How do they measure it? I hope you know that. Perhaps I should allow somebody to speak on this, because I want this to be related to your common experience. Can somebody speak on that? How do we measure, you know, the goalpost when we are playing corridor football?
We measure by feet.
We measure by feet. Hockey post.
What do we have different people person? If we have two people measuring, will it be acceptable or not?
No, sir. No, it won't be acceptable. Only one person.
It cannot be acceptable, sir.
Why not? Why should it be the same person?
They don't have the same feet.
I think they
don't have the same feet measurement.
Okay, they don't have the same length of foot.
Yes.
If the room separates of the same measurement can be used to do that, sir.
Yeah. So now the length of the foot of the person measuring here is what? Based on this discussion, what is it now?
It's feet. It's measured in feet.
What is the generic term? What's the term that we can use?
That's the unit.
It's the unit of measurement.
To measure what?
Unit of measurement. The unit of measurement.
To measure the length of the goalpost.
Yes. Now here is what I said by definition of measurement. The length of the person's foot is compared with the length of the goalpost to be measured. Does that make sense?
Yes.
Does it make sense now? So that is why I say measurement is an act of comparing what is measured with a fixed quantity of the same kind. So we are comparing length to length, mass to mass, volume to volume, and so on and so forth. All right?
Yes, sir.
All right, so let me mute all now that you know what I'm doing. So I will round this up briefly in another 2 minutes. So now you know. All right. So now that you know what I mean by measurement and units of measurement, I said a fixed quantity with respect to which other quantities of the same kind are measured is called unit of measurement. Examples have already been given. So if we are talking about the capacity measurement, a cupful of rice, okay, a basket full of tomatoes, and so on. So the basket full of tomatoes is a unit. A cupful of rice is a unit. And then with this, we can tell how many such cups are found in a bag of rice. So that way, we will be able to say 20, 30, 100. So we have now expressed our observation in terms of numbers. Take note of that. The essence of measurement is to be able to express an observation in terms of numbers, not by subjective description that, okay, it's very large or it's very small. No, you said it is 2 meters tall, 50 liters tank, and so on. Now, to avoid disagreement, as you rightly pointed out, we must agree on the standard of the unit. For the corridor football, you said only one person. So that means by agreement, you choose the person that is going to measure the goalpost. That becomes the standard. That becomes the standard. Standard is a unit, of measurement that is chosen by consensus, by agreement. It's chosen by consensus or by agreement. Now, in science, in physics, the standard of unit is that defined by the International System of Units, SI units. So the SI unit becomes the standard. That's why we call it the SI standard. It is a metric system. It is a metric system that is based on base 10 of measurement, of counting. The system defines 7 fundamental quantities, which you have already listed. See them there. So you have them there. So you have already listed this. Now, of these 7, the ones that we are going to use mostly in mechanics are length, mass, and time. And these are the most relevant there. Now, we can also talk about the multiples and submultiples of the fundamental quantities or units, if you like, the fundamental units. Look at them here. So we have theta, 10 raised to the power 12, or 10 raised to the power 15. Let me increase this. Tera, capital P here. Tera, 10 raised to the power 12. Giga, raised to the power 9. Mega, raised to the power 6. Kilo, raised to the power 3. Hecto, raised to the power 2. Deca, raised to the power 1. Now, deci, raised to the power minus 1. Centi, raised to the power minus 2 of a meter. So if I'm writing 40, let me write this down. 40 cm. That's 40 centimeters. Is equal to what in meters? Is equal to what in meters? How do we write it? In standard form. I want us to answer that. How do you write that in standard form? These are some of the sources of error in your calculation. That's why I'm asking that. How would we write that? 40 centimeters can be written how?
Yes. As 4 meter.
Huh?
As 4 meter.
4 meters.
It's 4 meters. 40 cm is equal to 4 meters.
Yes.
What?
4 times 10 raised to the power 1.
4 times 10 raised to the power 1.
0.4 meters.
Is that correct?
0.4 meters.
Meter.
0.4 meters.
0.4, sir.
4 times 10 raised to the
0.
power
In standard form. In standard form. You have not looked at it.
0.4
Please pay
meters.
attention to what I'm doing.
0.4. Okay.
0.4.
40
1000
times
cm equals
10
1
The
raised
meter.
to
standard
power. 4 times 10
Two.
raised to power.
Sir, mute.
4 times 10 raised to
40
power minus
times
1 meter.
All right. Now it is obvious that most of
4
you.
times 10 raised to power minus 1.
Now, can you see that if I given this in an exam, some of you will argue that the TMA or in a TMA question, because we cannot do this now, you will think that the answer we have given is wrong because we do not know how to express this in standard form. Somebody did answer 0.4 meters. But that is not the standard form. All right.
4 times 10 raised to power minus 1 meter.
Minus 1.
All right.
Minus 1. Who made that Boki?
Now let me mute everybody. Let me mute everybody.
So how do you get
going
this
to answer
material?
it, and you have to pay attention.
How do you get this
And
material?
I think with this, I may most likely, when we have done this part, we will finish and close for today. So this is, you see, I can write this as 4.0. I mean, we can write this as 40. Let me write it first because it's in cm. Let me write it first the way it must be written. One of you got it. You said it could have been written as this. 4.0 times 10. That's what you are saying. Raised to power minus 1 meter. I don't know if that's correct, but what this means is this. This is 40 cm, means 40 times 10 raised to power minus 2 meters, because I did say that centi is 10 raised to power minus 2. So once I say 40 cm, it means 40 centimeters. I beg your pardon. Meters. All right. So this is the one I am referring to. This is the one. This is the one. Okay. So this is the one I'm talking about. This one. So 40 cm means 40 times 10 to the minus 2 meters. All right. If I shift the decimal point to the left, I reduce this by 1 or increase this by 1, I beg your pardon. So that's going to give me 4.0, all right, times 10 raised to power minus 1 meters. So she was correct. The lady that said 4.0 times 10 to the minus 1. But the emphasis here is that if I'm saying 40 centimeters, it means 40 times 10 to the minus 2 meters. If I say 3 centimeters, it means 3 times 10 raised to power minus 2 meters. All right, so that's what I intend to draw your attention to. So you understand that now. Take note of that. These are simple things that come into your calculation. All right. All right. Now, finally. All right. So now, before we close, so you understand what I mean by, you now understand what I mean by centi, milli, 10 to the minus 3, micro to the minus 6. All right. So I think I will stop at this point. In the next class, I'll post this to you, and then we will take a look at. I want you to go back and read up to chapter in your hard copy. That is the heat and properties of matter. You should read up to unit 5. Please read up to unit 5. Read up to unit 5.
Sir, please, how can we get
Thank
this
you,
recorded
sir.
video, sir?
Thank you very much, sir.
No problem.
Thank you, sir.
How can we get
Thank
Please
you.
pay attention.
Hello,
Let me
sir.
do it.
Please,
I'm
recorded
going to
video
answer your question. Be patient.
And
and
the material.
I didn't understand whether an assessment you were explaining a bird fly from social frame. I did not understand.
Now, right.
A round of applause for our lecturer.
I mean, read up to unit 5. That's
Hello, class, please.
So when
everybody's talking, no one is talking.
I'll be solving
Sir,
problems.
can we ask a question?
Pay attention
Yes,
and let me
class.
finish what I'm saying. I'm directing you on what to do.
Okay, sir.
You have to read up to unit 5. So when I come, I will be solving problems in these units, concerning these units. Strictly, I will be solving problems. I'm not coming to teach anything about gas laws because they are known to everybody. I'm not teaching anything on thermal expansion because it's known. I'm not teaching anything on thermometry. I think the only part that I've explained a little bit might be the method of fusion. That is the method of determining specific capacity and so on and so forth. So we'll solve problems basically. So if I solve problems, it will be as good as I have presented that chapter. So those problems will illustrate. I will select some problems based on the content of this material and, of course, the nature of the TMA questions that you may most likely be expected to answer. That's what I will do. So that I will also try to present the part that you have the course material online, which you may not have the physical copies. So I'm going to take questions. Princess Blossom, quickly. Those whose hands are up, those are the ones I'm answering.
Please, sir, how can we get it? I didn't understand it, please, sir.
Who is speaking now? Blessing Blossom. Blessing Blossom. Now, Ben, what's Ben? Who is Ben here?
Hello, sir. Please. Hello, sir. Please, how do we get this material? This content is not in what I have.
I'm only going to listen to those. Ben cannot answer. Titus.
Sir, yes, I am Titus, sir.
Dankwa.
Yes, sir, I am Titus, sir. My problem is the content that you are talking about is not in our materials. I don't know.
It did not come to us.
Now it means you have not listened to what I explained.
Okay.
The questions.
Let me give you one.
Now pay attention to what I'm going to say now. The TMA questions that I have given are based on the content that you have in your hands.
Okay,
the
sir.
examination questions may not be said by me. Are you listening to me?
Yes, sir.
The examination questions may be said by anybody. And if the person chooses from the mechanics, in addition to the heat and properties of matter, you asking questions now will say that this was not taught. So I have explained ab initio that I am explaining that content so that you will be able to answer any question that comes from there. In any case, the title of this course is Elementary Mechanics First, Heat and Properties of Matter. So what is the mechanics? So it is not my fault. It is not my fault that mechanics was not included in what is it
okay, please, sir,
so
can you
I have done justice.
Particular one you have.
You will not pay attention now that I'm talking. I'm going to shut you down now very soon. I am telling you that the content that you have here is what was printed. And I have limited your TMA questions to the content of your material. But I may not be the one that will solve your question because people are usually set questions. So if the person has set questions in other aspects, like mechanics aspect, at least I will be vindicated that I prepared you for such questions.
Yes, sir. Thank you, sir.
Now, to answer your question, those course materials, this course material, the part I'm talking about is found in noun courseware, elementary mechanics. So go there and download it. I think if you go to the course page, I must have also attached it. I think I've attached it. I've even attached additional materials to help you in both aspects. I've attached materials there. Answers your question.
Please understand the first assessment, the one you were explaining. Fly from the frame. I don't know how to solve that.
So can I ask you a serious question? I need your
patience. Those who answer all right. Hawa, Aderi, Big Ben.
Sir, please, how can we get the recorded class, please? That's what I'm asking.
It's on the course page.
It's on our dashboard, on your dashboard.
Now, let's see.
Go to the course page to find it. Zenob, Mohammed.
Sir, can I ask a question?
I'm a paying patient. I need to understand the assessment. So if I'm working on it now, it will be confusing for me.
Go and read up now.
Hello, sir.
Zenob Mohammed.
Zenob, go and check the course.
Sir, my question is that please, how can we get these slides that you taught us now?
How can we get what?
This slide that you taught us now.
The course material is found on the noun courseware, and I think I've attached it to your course page. If you don't find it, when I'm sending this I'll also type additional copy.
All right, sir. Thank you.
Thank you so much, sir.
Hello, sir. Can you hear me? What she's asking is the slide that you used to teach this evening, not the course material.
No, wait now.
Zainab, the Allah, now making message. The WhatsApp.
Olajide praise. You are not paying attention, and I'm just calling those Yakubu praise.
Please, sir, please. Those reviewed course materials.
Olajide praise,
Yes, can you hear me?
Olajide,
we can hear you. Go ahead. Okay, those reviewed course materials, please can you list them for us? It's confusing someone.
What do you mean?
Like apart from pieces, is there other one, maybe like pieces 191 or that? Are they reviewed as well?
No, I am not. No, I'm not. You cannot hold me responsible for other courses. I'm not the one teaching them. I think I'll be confusing you the more by telling you you cannot come and talk about 191 here. This is a class of PHY 101. So why do you hold me responsible for that? All right. So I can list the materials that are related to
this class.
Come again.
When can we get the recording of this class? I checked my page. I don't know how to get it.
How to do
You will
what?
find it after the class. You will find it after the class.
Where?
On your email dashboard.
Our lecturer.
All right.
Not
everybody. We have come to the end of this class.
Sir, please, I have my question.
It's not everybody that knows where to get